Okay, so before I start talking, I'm going to give some disclaimers, caveats. The first thing is that I'm a computer scientist. So my attitude towards things may be a bit different than the attitudes of logicians. In particular, I view these things mostly as engineering problems. So I'm interested in understanding deductive reasoning only for the purpose, essentially, of building systems that reason deductively. So I'm going to make some modeling choices that maybe people with a different philosophical orientation will find objectionable. And if that's the case, I encourage you to object, and then we can hash it out. One, two, pardon the uneven presentation, as I hope you'll forgive me when I spend a long time belaboring things that seem obvious, and then also forgive me later if what I say is incomprehensible. And also, another feature of being a computer scientist is that I'm used to whiteboards, not chalkboards, so pardon my handwriting. I hope it will serve to evoke the memory of what I said, if nothing else. Okay, so what I want to talk about is truth. And again, as an engineering concept, I don't really care about truth philosophically. What I care about, the reason I care about truth is because it allows us to express useful concepts, or concepts that we want to use in reasoning. So in particular, I want to be able to express concepts like, if Bob says something, it is true. That is, I'm interested in building systems which can learn a generalization of this form inductively, which can then observe that Bob said something, can then conclude that that thing is true, and then can make the one additional step that not only is phi true, but phi. So formally, I'd like to have some predicate t, which acts on quoted sentences, where this is some suitable representation of a sentence inside our theory, such that t of phi is equivalent to phi for each phi. This is what I want. And again, the virtue of such a predicate is that it allows me to express sentences of this form. Yeah?
Is this going to be like a dequoting operator that just takes the quotation of a sentence and turns it into the sentence itself?
It's basically what this would be doing. Sure. And again, the virtue is that we can then quantify over quoted sentences. And in practice, of course, I wouldn't really want something like if Bob says something it's true, I'd want to say something like when Bob says something it's probably true, or this constitutes evidence in favor of the truth, and so on. Okay. So there's some trouble with trying to make a definition of this form. It's been long recognized. Namely, by diagonalization, we can construct some G, which is equivalent to not truth of G. And after having constructed such a G, this is also equivalent to not G, which is a problem. Right, so the existence of such a predicate leads to paradoxes of the form this sentence is false. So this is a sort of standard problem which any theory of truth has to contend with. And again, the criterion I want out of a solution to this problem is that it should allow me to do all the tasks that I would like to do using these sentences. That is, it would allow me to follow all the chains of reasoning that I could follow. It will allow me to express all the ideas that I could express. So with that in mind, some possible solutions. One solution, which is not super common, but is sometimes done, is to prevent diagonalization. That is, I could consider a theory which cannot construct a G which is provably equivalent to the truth of not G. And there's obviously some problems with such a theory for many purposes because this operation is a very natural kind of logical operation. Namely, it basically consists of applying some operator to its own quotation. And I can't really form an expressive and useful theory which prevents diagonalization. Or at least I don't know how to form a theory that's useful for my purposes which prevents diagonalization. So the select solution would have some hierarchy of languages. For example, I could imagine that this sentence lives in some level of a hierarchy, and that when it refers to says something, I mean that he says something in a lower level of this hierarchy. So maybe I have some sequence of languages, L0, L1, L2, and so on, each of which contains a truth predicate for all the preceding languages. And again, I don't know how to make this solution work for the kinds of operations I want to do. So I want to imagine that Bob is just saying something in language, and I don't want to explicitly say that the things he's talking about lie in a different domain than the things that he's saying. Or maybe to make this problem more stark, I don't really want to say sentences like this, probably. I also want to say sentences like this. I want to say that if I think something is true, then it probably is. When I express a sentence like this, it needs to refer, or it's sort of quantifying over thoughts that I can think. In particular, it's quantifying over this sentence. Right, so I don't want to use this solution which explicitly forbids self-references. Don't worry if that's encrypted. Okay.
What about languages that let you do impredicative quantification, but not referring explicitly to their own self-quotation?
What do you mean by this? What's an example of such a system?
So the one that I'm wondering about is type theory, where you need all of your variables to be well typed. But
so
you're
if
allowed
all of my variables are well typed, then I have this, like when I say if I think something, etc. What is the type of the thing that I'm...
So you could quantify overall propositions, and you could say something like, I think X is a proposition, and so I think is a function from propositions to propositions. If I think something would just be rendered as for all propositions X. If I think X, then...
yeah. So we have like, I think, which is some map from propositions to propositions. I want to say that there's some function.
So then the sentence, if I think something, then it's probably true, would be rendered as something like, for all propositions P, if I think P, then P is probably true.
I don't see how to make... So it's possible this works. In standard type theories, you can't do constructions like this, so you have to like attend to the typing of the variables, and so something that's universally, something that ranged over all propositions, including that proposition, would fail. Just the same reason, like the same diagonalization works in an untyped type, or in a type theory. Like there isn't a type of all types in the type theory. Like so, if a sentence, if Bob says something is supposed to be a proposition, then I would like this sentence itself to be a proposition.
Yes, and if prop is impredicative, then for all people in prop, something can still be a prop.
Yeah, so I should talk to you about this afterwards.
Okay.
Again, I will just be looking at it with an eye towards like, can it do the sorts of inferences that I would like to do?
Sure.
My impression is no, but it's possible I'm wrong. Okay. The third solution I was going to point to was employing some multi-valued logic or many-valued logic. E.g., I might take the attitude that such a sentence G simply has an undefined truth value. If I do that, I might say, well, I can have the truth value of phi being equal to the truth value of true phi. For example, I could just assign them both the true value undefined whenever I ran into this kind of self-reference. One problem with that solution, say in the case of a three-valued logic, is that if I feed in an undefined or a sentence whose truth value is undefined, I don't get back the statement that sentence is undefined. What I get back is an undefined answer. So similarly, I could try and run this over, say, a 0-1 valued logic or continuum valued logic, and I still can't ask questions of the form like, what is the truth value of phi? All I can do is say, is phi true? And I get back some answer, which is itself indeterminate. So what I would like to have is I would like to have this predicate t actually tell me the status of sentence phi. And this is not something one can obtain, isn't it? At least it's not something one obtains with standard approaches to many valued logics. I can run through an example of this much more explicitly after giving the rest of the presentation. I don't want to fill in the technical details right now. Okay, so this is basically the motivation or the motivating problem. Okay, so now I'm going to bracket that for a while. I didn't have any questions about this set, or what I'm after, barring the one that we've currently set aside about predicative type theories. So next I'm going to talk about probability. Again, I'm interested in probability because it's a language that seems to be very useful for reasoning. It seems to be like a uniquely good formalism for expressing and reasoning about our uncertainty about the world. So I'm going to say that instead of judging sentences as true or false, I'm going to assign them a probability 0, 1, which at the moment still looks very much like a many-valued logic. That is, I'll have some function p which maps from a language L to 0, 1. And I want to say that this assignment of probabilities is coherent if it satisfies some basic consistency conditions. So in particular, p of true should be 1, p of false should be 0. If it's provable that phi and psi are equivalent, then p of phi should equal p of psi. And maybe one more. The probability of phi is just given as the sum of the probabilities of some exclusive events comprising. It's like finite additivity. A more true statement. Okay, so here I have some basic axioms that constrain the set of probability distributions I'll allow, or the set of assignments of probability sentences that I'll allow. I say that a probability distribution, or an assignment of probability sentences is coherent if it satisfies all 4 of these properties. It's an easy exercise. That P is coherent if and only if there exists some measure, some probability measure mu on models of P. Models. Such that the probability of a sentence is precisely the measure of the space of models satisfying that sentence. So intuitively, these constraints correspond exactly to like the possible world semantics we expect, right? There's some set of possible worlds, some set of models that may be the actual model, and the probability of a sentence is precisely the probability of the set of worlds in which that sentence is true. So we can pass back and forth freely between this understanding and this understanding. And this is just by compactness. Actually, I guess completeness is also interesting. Okay, so if we're going to work with probabilities instead of truth values, our original problem should be somewhat restated. That is, instead of seeking a truth predicate, which given a quoted sentence tells us the truth of that sentence, we now want a probability function, which given a quoted sentence tells us the probability of that sentence. I.e., we want a function symbol p such that the probability assigned to the quotation of a sentence is exactly equal to the probability that sentence is true. This is just precisely analogous to the statement. And if we had a function which had this, satisfied this sort of property, we could use it to express sentences like if Bob says something, it's true. Okay. The same trouble from before also still applies because I haven't made my job any easier in constructing such a P, I've made it strictly harder. Right, so I could still consider a sentence such as G is equivalent to P of G equals 0. And then if p of g is greater than 0, this implies that p of g equals 0. And if p of g equals 0, this implies p of g equals 1. And this is just because p of g is equal to 0. I guess I should say this sentence should be true almost surely. So now what we're talking about is we're talking about probability distributions over models. P is a function symbol, which is getting assigned to some function by our model. So this is a sentence. This is some real number. This is a sentence which can be true or false in each model. And I want to say that the set of models in which this sentence is true has probability 1. And in that case, this construction goes through exactly as in the previous case. Are there any questions about this notion? Is anything unclear about the definition?
I'm still a little bit confused about how you get from p of g greater than 0 to p of g equals 0.
So if p of g is greater than 0, then there's some real number that p of g is equal to, which is greater than 0. Let's say it's like epsilon. Mm-hmm. In that case, by this property, we should have p of g equals epsilon with probability 1. And if p of g equals epsilon, then p of g is not 0. And so g is false. So g is true with probability 0, so p of g equals 0. And then similarly on this side. Okay, again, so here we've just made the job strictly harder than it was before. So probability has an advantage, or one significant advantage over truth, in that the space of probabilities is like this set 0, 1 has this nice topological structure on it. And I'm willing to accept very small deviations in the probability that I assign to a state. So if I build a system, I'm fine if the system makes arbitrarily tiny errors in its estimates of the probabilities of events. So I've made the problem harder. I'm now going to make it somewhat easier. So my relaxation of the notion of a probability function. And the relaxation I want to imagine is that I have some box implementing P. I feed into it some quoted sentence, and instead of getting out the actual probability, I get out some arbitrary approximation to finite precision. Okay, so this is like what an actual computer approximating P would look like. Right? I would not be able to just get the probability. I would get some sequence of bits, which is giving me increasingly accurate approximations to the probability. So with this picture, what I imagine happening is I imagine that if the probability of a sentence is in some open interval AB, then this thing should tell me that it's in that open interval. So I can get a sufficiently fine approximation to determine that. So this motivates this weakened notion of what I mean by a probability function. Just a function which is, for every open interval that actually contains the probability function assigns a number in that interval with probability 1. So conversely, if probability of P is in some closed interval with positive probability, then P of P is in that interval.
Can you give an example of such a function other than just the point and the mapping to the probability itself?
Yeah, so this is going to be true as a logical statement. That is, for each A and B, this is going to be true. But it's not going to be true that for all A and B this holds. Right, so what's going to happen is for every actual pair of rational numbers A and B, every rational interval that contains this point, the value that P outputs is going to be in that interval. But it will be off by some formally infinitesimal error.
formally infinitesimal. So you're saying that the output of P need not be an actual real number.
It will not be a real number.
Ah, thank you.
Yeah. Yeah. So it's sort of like imagining there's a difference between 1 and 1 and.
Yeah.
Yeah.
It can be a surreal number or something.
Yeah.
Okay.
That is exactly what happened.
Oh. All right.
Well, I mean, I won't actually go all the way to the real numbers because that won't be necessary.
Okay, fine.
Okay, so this is sort of a relaxed notion of what I might mean by a probability function. And again, from the perspective of designing a system, I think this is perfectly adequate for me. Like, I'm happy if instead of being able to make a move from P of phi is 0.3 to the probability of phi being exactly 0.3, I can just move to the probability of phi is very, very close to 0.3. Because I'm fine if there's these infinitesimal errors in my probability assignments. In fact, if we're used to programming, like making exact comparisons between floating point numbers is bad form anyway. It's like not even something that it would occur to me to do. Okay, so running through some simple examples. If G is equivalent to P of G is less than a half, then P of G equals 1/2. I.e., P of G is in every interval containing 1/2 but is less than 1/2 half the time and greater than or equal to 1/2 the other. And in general, what's going on is that the models we produce are going to be non-standard with probability 1, and we're going to have that P of G is equal to P of G plus some epsilon. And this epsilon is going to be formally infinitesimal, i.e. it's less than every actual real number, and it's going to be stochastic.
Are most models of logical theories non-standard models?
Yeah, but maybe it depends a bit on usage, but pretty much all of them.
So what's the stochastic element in the above example?
It's like a coin. You can imagine in this case it might be that it's 1/2 plus some formal infinitesimal, or 1/2 minus 50-50 either way.
Oh, okay.
Or maybe it's a normal distribution with infinitesimal variance centered on a half. Whatever. Yeah.
So can you only find such symbols P in almost all of the models? And for example, in the standard model or the intended model, you couldn't find such a symbol?
Yeah, so there's no model which has like the normal set of real numbers such that it contains a P satisfying this property. You need to have some number epsilon which is smaller than every rational or every actual real number if you want to satisfy this property for every real number. I think philosophically this might be somewhat unsatisfying. From the perspective of building a system, it's really not so bad. I also don't find it very philosophically unsatisfying. Maybe that's because I've been staring at it for too long.
So I guess it's going to be fair game to ask about building systems at the end.
Yeah.
Okay.
So unsurprisingly, the theorem that I want to prove is T is any theory. There exists a coherent P such that So for this property, this relaxed property I specified, there actually exist models. There actually is a distribution over models which satisfies that property. Any questions about the statement of the theorem or anything that's happened so far? So the way the theorem is going to go, or the proof of the theorem is going to go, is I'm going to consider a certain revision operator, which starts from a distribution P, and then creates a revised distribution P prime that is sort of fully informed about P. Then I'm just going to find a fixed point of that revision operator. And that will be a distribution that's fully informed about itself in the sense of satisfying this property. So formally, consider the map F, which sends P, is set P prime. Right, so we want to send P to the set of P prime which are consistent with P. So it sends P to the set of P prime such that for every A, B, and phi, P of phi in AB implies P prime of P of phi in AB equals 1. So again, we imagine these P prime as being probable distributions for which this symbol little p is referring to this blackboard. And then our goal is simply to find some p which is inside F of p. So to do that, consider the product topology on 0, 1 to the L. Right, so it's the topology of pointwise convergence on the space of all assignments of probabilities to sentences. The space of coherent keys is closed, convex, and compact. Closed because it was defined by some equalities, some strict equalities, and the intersection of any strict equalities is closed. It's convex because you can mix together two probability distributions. It's compact because the space is compact and it's closed. And furthermore, if this theory T was consistent, then there's some probability distribution that satisfies that is coherent. Namely, it's the probability distribution that assigns probability 1 to any complete theory of T, complete extension of T. Okay, and so then claim F has a closed graph. And if we have this claim, then by standard machinery from fixed point theory, we can obtain some P which has this property. And if you don't like the topology, then we could have done this logically as well. Right? Instead of using the compactness of this topological space, I could have just used logical compactness together with the fact that for any finite subset of sentences, a normal finite dimensional fixed point argument would give me some P inside of P locally. And then checking this is just straightforward. So this condition amounts to, given some set Pi that converges to P, Pi prime converging to P prime, such that Pi prime is in F of Pi. I need to prove that F, or that P prime is in F of P. So this is precisely what it means for a function to have a closed graph. Given some sequence of points, and some sequence of points that are in their respective images, the limit of this sequence belongs to the image of the limit of that sequence. This is not a very enlightening argument, I think most of the work has been done just by setting up the problem in this way, essentially. To verify this property, just observe that if A is less than P of phi is less than B, then A is less than Pi of phi, less than B for almost all I. So Pi prime of P of phi in AB equals 1 almost everywhere, and then we take the limit and we get this argument. Sorry if that's too low for people to see.
Wait, just so I'm clear about something, this fixed point argument is operating only on standard real numbers and not on the non-standard ones?
That's right. All of these objects are actually functions in 0, 1 scale. So these are real value functions.
So in some sense, you sort of introduced the non-standard numbers like for definitional purposes, and then you just got rid of them.
That's right. I mean, the non-standard numbers,
dispensable to them.
They never appeared in the argument. It's just like if you look at the actual models corresponding to the assignments key that we produce, they contain these non-standard numbers. Just because, like, if you produce a model by a compactness argument in general, you're going to typically introduce some random extra non-standard objects.
Wait, so when do the non-standard elements appear then? Is it in passing from the finite dimensional to the infinite dimensional case?
Yeah.
Ah, thanks.
Is the fixed point machinery constructive? Does it give you an actual probability distribution that's computable?
There are no computable coherent distributions, even ignoring this property. Because, for example, they assign probability 1 to all the theorems of your underlying theory and probability 0 to all the negations of theorems, and that's not possible to do computably. So these objects are very uncomputable. They're sort of more like what is true than what I'll describe why again. So you might think these objects are not of interest for actually building a system, given that they're incredibly uncomputable. And I'll describe in 1 second how they can be used.
Well, actually, can we say something more about their degree of uncomputability? So, like, is there, are they anywhere in the, arithmetic hierarchy, or are they sort of above all of that?
Yeah, I can construct such objects P using a halting oracle.
Ah.
It may be better than that. My guess is that the fixed point theorem needs weak Koenig's lemma, not arithmetic comprehension, and so possibly low, like having no jump.
Oh, okay, well, just the fact that you can do it with a halting oracle already tells me something. Okay, good.
Yeah, and so again, Cameron says it's probably even weaker.
All right, fine,
well,
fine.
Yeah, no.
Okay, fine.
Okay, and so that's it. So I guess the fixed point theorem I want to appeal to is Kakutani's fixed point theorem. It says exactly what I needed to say.
So the non-computability, does it come in from the fact that is element of some interval in the reals, is that an undecidable property, or does it come in?
It just comes in from, like, a coherent P is already a very uncomputable object. A coherent P is already encoding the provability of every fact consequence of counterarithmetic.
Right, but so what I'm asking is where in constructing the coherent P do you give up computability?
I give it up when I say that, like, f of P is non-empty.
Okay.
So f of P is non-empty because there's some theory that's consistent with these facts, but I can't have a predicate which actually tells me whether something is a theorem versus the opposite of a theorem.
Also, the zero jump, the halting problem, like you said, should be something like relative to t for the reason that you mentioned. Right? Like if t is nasty, then like get the turn jump a bit.
Yeah, okay. The complexity might depend on t. The actual use I'm going to make of this object doesn't rely on any, like I'm computing anything about p. I'm just going to use the fact that a certain axiom schema is consistent. Right? So I'm not going to have to construct any objects.
So in particular, if we can compute it with a halting oracle, does that mean we can get arbitrarily good approximations to it in some sense?
In some sense.
Okay.
Yeah.
Well, it's not clear though we can like get arbitrarily good approximations to the reflection schema that way, or if that's true, it's yet to be proven as far as I know.
Okay.
The reflection schema being what comes out of the fixed point argument?
Whose existence was established by the fixed point argument.
So I'll call this schema like R or something for definiteness. Okay, so a different way of stating the theorem that I've just proven, which is more useful, or closer to being useful. Corollary. It's barely even a corollary, really. Given any theory T, I can adjoin a symbol P. And the axiom schema, I'll adjoin a function symbol P. And the axiom schema for all A, B, B. Hey, the same properties over there. All those things are. So it may not be clear exactly what I mean here, because the statement R involves this blackboard P, which is not a normal logical operator. What I mean is simply that it will be impossible to derive a contradiction. Using the properties of coherent Probabilistic distributions. Provided the T itself was consistent. So what I imagine doing with this theorem is not actually using this object P that I've constructed. I imagine building a system which uses axiom schema R in the same way that we might use like this dequotation schema with a truth predicate. And this theorem guarantees that I won't introduce any new contradictions. As long as the underlying theory was consistent, I won't be able to deduce a contradiction from the new theory. Okay, so at this point I'm going to jump a bit and start talking about, like, very briefly sketching how one might build a system that uses this kind of information to make judgments, which you couldn't make without it. So if anyone has questions about anything that's come so far, now is a good time to ask.
Do you also get from this that P satisfies your properties that it's coherent? Like that?
That this P does?
Yes.
Yeah, we can get that. What we don't get, which we might want, is for P to satisfy this property for all V A and B. So little p does not satisfy this property. If I replace this by little p and this by little p.
What little p is the symbol?
Yeah.
Okay. But it does satisfy things like big P of little p of true equals 1.
Yeah.
That's 1?
Yeah.
Okay.
And the reason little p can't satisfy this property is that the errors are infinitesimal from the outside, but from the inside they just look like normal real numbered errors. Sorry if that's confusing. Any other questions about what's come so far?
So maybe it would be helpful to just see a couple of examples, like what happens when we try to render the paradox of the liar. Like, do we just get a truth value of a half?
Yes, this was the example of
okay.
G is equivalent to P of G less than a half.
Oh, okay, so that's your rendering of the liar paradox?
Yeah, so we can also...
G, if it not PG or P of
Right, I would have said that like
this.
P, the truth value equals 1. The probability of truth equals 1 minus the probability of truth. Like, can we express something like that?
Or G if
that would be
if P of quote not G unquote?
Well, okay, so we could do something like this, which is sort of the other reasonable interpretation, and here what we get is P of G equals 0.
Okay.
And what's true is, at least from the inside, P of G is some infinitesimal.
I see.
So it's not the case that it's equal to 0, but it is the case that it's very, very close to 0. But it satisfies our.
Yeah.
And I think that G, if and only if P of quote not G unquote would be 1/2.
P if and only if P not G. Yeah, that would be the same.
No, it would have to be sub equal something, doesn't make sense. Or like P of G, or
like this, we can go through cases like this, and with one variable they all look just the same. If we get into like a whole system of self-referential GIs, I go through more complicated examples. Then we might introduce not only non-standard rational or real numbers for the values of P, but non-standard integers to make the examples work.
So I think one of you said before that you don't have an argument yet that you can do arbitrary approximations to the reflective schema. Is there a reason that you can't push through the approximations to your initial non-empty, the fact that f of p is non-empty through the fixed point argument?
Well, you can approximate these all in the sense of like point-wise convergence eventually, in the same way that you can often approximate objects of this type, and you can continue to do that even if you have this schema, I think. Like just consider larger and larger fragments of the schema, each one you can do this for, and then as you take the limit for each sentence, you get back right there. So I believe you can get point-wise convergence to this computably if you want. I don't know if it's helpful. Okay. So here's an example of a system. We're assigning probabilities to propositions. To give an example of the sort of thing I have in mind as an application. So I'm just going to write some pseudocode. I'm going to write pseudocode relative to a halting oracle. I hope people will forgive me. In practice, I would imagine replacing a halting oracle by some large amount of computation and then weakening the consistency conditions I'm using. But for now, just imagine we live in a world where we can invoke a halting oracle some finite number of times, and where the rest of the world is so complicated that invoking a halting oracle a finite number of times is not so useful. Like, the problem you care about in the real world invokes a halting oracle many times, or perhaps is even farther up the arithmetic hierarchy. So using a halting oracle, I'll define Q of phi as follows. So I'll initialize a set of propositions S to be T, where T is some theory that I believe. Then I'll repeat the following process. Pick psi at random from L, using something like a length prior. So I'll pick some formula psi, which I expect to be short with higher probability. Something like P of psi is proportional to 2 to the negative psi, or something. So I'll pick psi at random from L. If S proves psi, or S proves not psi, then I'll just continue, i.e. go back to the top of the loop. Otherwise, I'll flip a coin. If heads, then S becomes S union psi. If tails, then S gets S union not psi. I will keep doing this until S proves phi or S proves not phi. If S proves phi, I'll return true. If S proves not phi, I'll return false. I use the halting oracle, obviously, in these steps, where I check to see if the theory proves some arbitrary assertion.
Well, what does it mean to choose an element of L uniformly random? L is what again?
Sorry, this is the language, the set of all propositions.
Okay, but how do you choose a uniformly random?
Yeah, so I'm imagining something like probability to the
sorry,
negative.
okay.
Yeah, no trouble. Okay. And then I'll define P of phi to be the probability Q of phi outputs true. So this is some procedure which, using a halting oracle, builds up a random theory in a certain way, and then it just outputs the probability this random theory entails phi, as opposed to entailing not phi.
Is that computable?
No. I mean, it's computable with a halting oracle.
Actually, even with a halting oracle, it's not obvious.
Yeah, so with a halting oracle, it is computable. And you can do that just by simulating branches of this tree, and you're accumulating more maths for phi and not phi, and eventually they'll add up to 1, so if you want an epsilon approximation.
Oh, all right, so an epsilon approximation.
We can also converge to this, I believe, by searching longer and longer for proofs.
Maybe.
Okay.
Again, assuming T is computable too.
Yeah. Yeah. So I guess all of this is only computable as computable as. So we have this definition of P of phi. It's another easy exercise to prove that P is coherent in the sense I described above, i.e. it corresponds to some distribution over models. That's just because what it's doing basically is sampling a complete theory. So it corresponds to a natural distribution over complete theories. And the basic premise is that, I don't think this is a particularly sensible prior, but it's just kind of like someone's prior over the truth of mathematical statements. Before you've interacted with the world at all, you have some beliefs about which mathematical statements are likely to be true and which mathematical statements are likely to be false. As you interact with the world, you condition on the truth of facts that you learn, and then you'd have some beliefs about the other facts which you have not yet learned. So for example, P of n plus 1, conditioned on P of 0, and P of n converges to 1. As n approaches infinity, as long as t doesn't prove not for all n. So this is the property you might expect from someone's distribution over facts. If I tell you that phi of 0 is true, and then that phi of 1 is true, and so on up to phi of n being true, eventually the probability of assigned to the next phi being true should become very large. Like you saw one white swan, another white swan, and so on. Eventually the probability assigned to the next one being white becomes close to 1. So the reason I bring up this example is because this is the sort of system in which I could plug this kind of probabilistic reflection scheme. So I'll sketch briefly how to do that, and then I'll be out of time. So I'm going to modify this procedure. Instead of having a set of sentences which I know to be true, I'm going to initialize it with a map P. And P of psi is going to be the singleton 1 if T proves psi. Otherwise, the whole interval 0, 1. So what I'm doing now is I'm imagining a procedure which entertains a space of possible probability distributions at each step of its execution. Inside the loop, I'm going to do inference, deductive inference. So I'm going to update P of psi to be equal to P prime of psi over P prime that agree with P. So P prime of phi equals P of phi for all phi, and P prime is coherent. So I did the initial step was for each sentence, I came up with a space of possible probabilities that sentence might receive. So each sentence, which was a theorem, can only be true with probability 1. All the other sentences, we'll say at first, can be true with any probability between 0 and 1. So that was step 1 of the process. Then in the inner loop, the first step is I restrict the probability of each sentence to be something that's consistent with the other data I know. So for example, if something's negation was a theorem, it should only be true with probability 0. So right now I assign it the entire interval from 0 to 1. So what I'm doing in this step is I'm considering the space of p primes that are consistent, I should say n, I guess, that are consistent with all the data I have so far, and which are furthermore coherent. And then I'm updating p of psi to be equal to that set. So this is like the smallest set of probabilities that I can constrain p of psi to lie with. Then I'll pick some psi at random from L. I'll set. I will draw P at random from P of psi. And I will update P of psi to be the singleton set. So in the old description, I chose randomly whether a sentence became true or false. In the new description, I'm choosing a random probability consistent with what I know and assigning that sentence that probability. So previously I said its probability could be anything in the interval, now its probability is exactly 0.6, or 0.6 was chosen at random from the interval. Having done that, I go back up here and I update P to reflect all of the consequences of that change I just made. So for example, if something else is provably equivalent to psi, it will also receive a probability of 0.6. And at the end of the day, now I'm going to use another halting oracle. At the end of the day, I output P of phi. So at every step of execution, P of phi is assigned to some set of probabilities. I run indefinitely. By the end of this procedure, P of phi will be assigned to a singleton set. I can also imagine outputting the intersection of all the sets. And I output that. And then I define P of phi to be the expected value of P of phi. And now to use this reflection schema that I introduced, I just augment this coherence property to also say that it also satisfies R. So I basically just change the set of deductions that I'm doing. Instead of being only logical deductions, I also allow myself to apply this schema, going from little p of phi to the actual probability. Okay, so I did not have enough time at the end to actually go through this. You can just ignore the last 10 minutes of the talk if they were too confusing, and hopefully it's 5/6 as good as it would have been. That's it. So if anyone has any questions, I guess feel free to ask now. Keep going.
Any more questions?
So could you say briefly how it happens that those conditional probabilities converge to 1?
What the argument is?
Yeah, yes.
So if you multiply all of these together,
Yeah.
you get into something that's smaller than p for all n p of n.
Right.
Like if you multiply together the first k of these, you get the probability of p0 and p1 and p2 up to pk.
Yeah.
This is lower bounded because it was possible that the very first step of the process, I chose this sentence and added it. So this is lower bounded. When you multiply these together, it stays above this.
Right.
So eventually they've got to converge to 1.
All right, good, good. And suppose that T does prove that not for all n phi of n.
Then it's confusing.
Okay.
I think this will still typically converge to 1.
Oh.
And assuming that T is consistent with saying sentences like for all n up to something extremely large, this is true. And then,
or for that matter, as long as it can like still semantically, as long as it like only has supernatural models with which will give it existence property.
Right.
well, it's a bit it's a pretty complicated condition for it to work if it entails this. I'm just going to assume.
Because I was thinking about, you know, a rational agent, even knowing that there exists an n where phi of n fails, might want to, you know.
Yeah, so for example,
the probability.
if you look at the P I actually described and you use like the busy beaver numbers,
Yeah.
then it will, to this proposition n plus 1 is the next busy beaver number, it will eventually, this will converge to 1.
Yeah. Yeah.
And so it will be wrong about that. So that's right.
Well, once every busy beaver.
Once every busy beaver number.
Yeah.
Well, not, I guess you'd have to use the busy beaver numbers relative to multi-oracle.
Yeah.
But
Yes.
other than that, that's correct.
Yes.
Any other questions?
When you add in the satisfies R, how do you know that you will always, that you never get the empty set.
So that's what we get from this. We always know there's at least one p prime consistent with these things, because we know that we didn't introduce any new contradictions by joining that reflection schema. So this set always remains on empty. That's exactly where we make use of the whole theorem.
I'm still wondering if there's a way to redo the whole argument, just getting rid of the non-standard analysis, since it disappeared in the end anyway, it seems. I mean, like in particular, like could we just sort of put a restriction on how you form the propositions so that you can't say, if like P is true if and only if its probability is 0 or something like that.
So I guess I can say two things about this.
Okay.
One, if you want to actually have errors such that the error exists and is less than epsilon for every epsilon, then you're necessarily going to be introducing some number smaller than every epsilon. So we can't do quite that.
All right.
We'd still want to get rid of the non-standard numbers in the sense of maybe for every epsilon we want to construct a model which has the standard real numbers inside it, or as its real numbers, but such that this reflection scheme is true up to some real error epsilon, like epsilon equals 110. And that I don't know how to do. I can write, if anyone here knows about fixed point theory, I can write down a nice fixed point theorem that would be equivalent to that, which is slightly different from most claims people try to prove. If anyone can prove that, that would be nice. I think I don't want to talk for another 3 minutes though.
Any other questions? Let's thank Paul again.